Alright, so in this video I will go over a section of chapter 5. So please read chapter 5 section 5.1 only, and the recommended problems are 55, 59, 61, 75 and 73. So in this chapter we will talk about heat. By definition, heat is the flow of energy. That is, energy transfers from hot objects to cold areas, or from hot areas to cold areas. So if you touch ice, your hand will feel cold. So the question is, why does the hand feel cold when you touch ice? The answer is, the ice will feel cold because heat is transferred from your body to the ice. You feel cold because your body is losing heat to ice. So like you were at this high energy, when your body loses heat to the ice, you become lower energy, and in that case you feel cold. Anything you touch that feels cold, know that it is consuming energy from you. Steam feels hot because heat is transferred from the steam into your body. So since your body is gaining energy, you feel hot. Is temperature and heat the same? The answer is no. Temperature and heat are not the same. Heat is energy transferred from a hot object to a cooler object. But temperature is a measure of the average kinetic energy of the molecules in an object. So every object has particles that are always in motion. So when you combine all the motion of these particles, that you can measure them using temperature as a measure. So by definition, it is a measure of the average kinetic energy of the molecules in an object. So that's the definition that we need to keep about temperature. The greater the kinetic energy of the molecules of something, the higher its temperature. So if you have two objects, one has high kinetic energy, the other has lower kinetic energy, the object with high kinetic energy is going to have a higher temperature. An example is boiling water and water at room temperature. We see that boiling water, there is a lot of movement there, and if you put a thermometer in there, you will see the boiling water will be at higher temperature than the normal room temperature water. Now let's look at this example. So we have two hot plates containing 2 beakers of water. We have a smaller beaker here, a larger beaker here. So the question is, we want to heat up the beakers, the water, from 23 degrees Celsius to 89 degrees Celsius in both cases. So the question is, which of the two between A and B will heat up first from 23 to 89 degrees Celsius? In this case, the answer is A. A will heat up first because it has less water than B. You will need more heat to heat up more water than the heat you need to heat up less water. But remember, in both cases, you are just changing from 23 degrees Celsius to 89 degrees Celsius. If heat and temperature were the same, we would need the same amount of heat to change from 23 to 89 in both cases. But since these two are different, we need different amount of heat in these two cases to change by the same temperature change. So you need less time to heat up A from 23 degrees Celsius to 89 degrees Celsius than you need for B. And if you use the same amount of heat, A will heat up first to 89 degrees Celsius before B does. So this shows that heat and temperature are different. If we continue, just try this in your room. Touch and feel different materials in your room. Let's try to touch a desk. Let's try to touch your book. Let's try to touch your couch. Let's try to touch a chair, the cloth part of a chair and the metal part of a chair, or the plastic part of a chair and the metal part of the chair, and see the difference, how you feel, and maybe predict the temperature of each. You see that a metal desk will feel colder than a wooden desk in winter. The opposite happens in summer. In summer, a metal desk will feel warmer than a wooden desk. We need to take note that it doesn't matter if these two are in the same room, they are at the same temperature, although they feel different. So we say both are at the same temperature in both the winter time and the summertime. So both are at the room temperature, or the temperature of the room. But why do they feel different? They feel different because the metal transfers heat faster than wood. So in summer, you will feel hot if you touch a metal. In winter, you will feel cold if you touch a metal, because there is a sudden transfer of heat in winter from the metal to your body. In summer, from your body to, that is in winter, from your body to the metal. In summer, from the metal to your body. So let's look at solids, liquids, and gases. These are the states of matter, and we'll talk about the changes that these states of matter undergo. These changes are always physical changes. So the first one is melting. In melting, the solid changes to liquid. In freezing, the liquid changes to solid. So these two are opposite each other. Evaporating, the liquid changes to gas. Condensation, the gas changes to liquid. Then we have sublimation, where the solid goes directly to gas. And deposition, where the gas directly goes to solid. So take note of these, be able to define each of them, and be able to do them in an exam situation. Energy and phase changes. Let's take an example of water. We know that water has hydrogen bonding. In the solid phase of water, the hydrogen bonding is at the highest. So the water molecules are strongly attracted to each other, that the molecules have they stay in specific positions, or they stay in a specific solid structure with the air spaces in between them. So the hydrogen bonding is responsible for the solid structure of the water molecule, or the solid structure of ice. Now, if you apply heat to the ice, you start breaking up these hydrogen bonds that we can see here, and the hydrogen bonds are broken, and then that solid structure also gets broken to have a liquid structure. The solid structure, water cannot flow. The liquid structure, with the broken hydrogen bonding, water will start flowing. Now, in liquid water, we still have that hydrogen bonding, but it is not as strong as in solid form. So we see that in liquid water, we have hydrogen bonding. If we keep up heating up the liquid, there will be a time when the hydrogen bonding is broken, and the molecules are lifted away from each other. Now this is water in a vapor stage. So that is at the boiling point, that is what happens. We have some liquid, we have some gases. The water molecules are lifted from this liquid phase into gaseous form, where the hydrogen bonds do not work anymore. So we see that if we consider these three states of water, we have lots of hydrogen bonding in the solid form, more movement between the molecules in liquid, but still we have some hydrogen bonding. The molecules separate and move freely in gas. So we need to take note of that. Now let's look at the melting points and boiling points. These are characteristic properties of materials that are defined by the energy flow. Normally we use a heating curve to understand what happens to the energy as we heat an object from solid to gas. So a heating curve can be used to determine the values of the melting and boiling points of materials. We will see how. Now, when you are heating up something, you start from solid, like ice. You start from solid, and then you reach the melting point. Then it becomes liquid, and then you reach the boiling point, and then it becomes gas. So we need to take note of this statement, a very, very important statement. At the melting point, adding heat does not change the temperature. All added heat goes into change of state. It's the same thing. At the boiling point, adding heat does not change the temperature. All added heat goes into change of state. So if you are boiling water and you reach maybe 100 degrees Celsius, you see that you can boil as long as you have liquid water in there. The temperature will still remain 100 degrees Celsius. It will not go to 101 because all the heat is used to change the state from liquid to gas. Now this is the heating curve. If we start with ice here, this is the heating curve of water, right? When you have ice, this is the melting point of water, which is 0 degrees Celsius. This is the boiling point of water, which is 100 degrees Celsius. When you have ice is usually at temperatures below 0 degrees Celsius. So if you heat up ice on the hot plate, you start raising the temperature of ice from whatever it was, whether it was negative 10 degrees Celsius or negative 15, you start raising the temperature up to 0 degrees Celsius. At 0 degrees Celsius, if you add more heat, the ice will start melting. But you can see that here that the temperature is not changing. The graph is flat. The temperature is not changing. And then when all the ice is dissolved, when all the ice becomes liquid, the temperature will start changing again. It will start rising until you reach 100 degrees Celsius. Now this is the boiling point. The water will start boiling. The temperature will not be changing. So we have a flat here also. After all the water has boiled, if you have something to capture the gas, you see that the temperature will start going up. But if you are not capturing the gas, this is where you end up with, because all the gas will go into the atmosphere, and we may not see a change, an increased temperature from boiling. So that's one thing that we need to know, that at the melting point, the graph is flat, the plot is flat. At the boiling point, the plot is flat because the temperature is not changing. But before melting, we see that the temperature is increasing, and also before boiling the temperature is increasing. After boiling the temperature is increasing. That's one thing that we need to know. Another thing that we need to know is what is present in the liquid, or what is present in a substance before melting. What is present at melting? What is present after melting? What is present at boiling? What is present at after boiling? So when you have ice, before melting, you only have solid. So before melting, you only have a solid. At a melting point, you have an equilibrium of solid and liquid. So some ice turns into liquid and some liquid turns into solid. So in this case, we have both solid and liquid at melting point. After all the melting is done, we only have liquid here at this point. So we only have liquid at this point, and then we reach the boiling point where we have another equilibrium, liquid and gas at the boiling point. After all the boiling is done, we only have gas. So we see that at A, we only have solid. At B, we have solid and liquid. At C, we have only liquid. At D, we only have we have liquid and gas. At E, we have gas only. So in terms of energy, the energy at B, we see that temperature is not increasing because energy is being used to break up the liquid structure. Oh, not liquid structure. Energy is being used to break up the solid structure because we are moving from solid to liquid. Here, energy is used to break up the liquid structure. That is, energy is used to evaporate instead of increasing the temperature. While here, the energy that we add is used to increase temperature. Here, the energy that we add is used to increase temperature. Here also, the energy is used to increase temperature. It's only these two positions where the energy is used to break up the structure of either solid or liquid. So let's take note of that. We need to be able to draw this for the exam. Or if I give you this in an exam, you need to be able to tell me what is present at A, what is present at B, what is present at C, at D, at E. You also need to tell me what is energy used to do here. What is energy used to do here? What is energy used to do here? Things like that. So let me go back to the explaining the heating curve. Before melting, we see that there is a temperature increase. We are heating up ice. The solid will be vibrating, so the solid vibrations increase because when you heat up something, there are vibrations that are happening, and the solid vibrations are increasing. That is before melting. In this case, there is only the solid present. At melting, heat is used to break structure, the solid structure. The solid and liquid phases coexist. So we have both liquid and solid present. The temperature remains constant. After melting, the temperature, we see a temperature increase because we are heating up the water now. Liquid vibrations increase. At this point, liquid only is present. At boiling, heat is used to break liquid intermolecular forces into gas phase. So we are breaking the liquid structure. Liquid and gas phases coexist. Temperature remains constant. After boiling, that we call superheating, we see a temperature increase. All right, forget about this. Solid and phase coexist. They do not. So this is a mistake. Remove this one. But temperature increases. Remove this. Kinetic energy of gas molecules increase. So it's only this and this. And at this point, it is only gas present. So let me emphasize again, remove this. Solid and liquid phases coexist. This one is for this part. So we can think about the melting and boiling points. Every substance has a unique melting point and a unique boiling point. And this is due to the strength and number of intermolecular forces of attraction between the molecules. So if a molecule has a lot of attractions, definitely you need more energy to melt it, or you need more energy to boil it. So if adjacent molecules are held together more strongly, then more energy will be required to separate them. This results in higher melting and boiling points. That's why metals, the ionic compounds, will need very high boiling point, because you are separating strong chemical bonds. Molecular compounds normally do not need high boiling points. So one thing that we also need to learn is that water is a liquid at room temperature. Ethane with the same size of water is a gas at room temperature. So the question is why? Water has strong hydrogen bonds that ethane does not have. Water has strong intermolecular forces to make it liquid at room temperature. That hydrogen bond is important. That's why ethane is not a liquid at room temperature, because it does not have that hydrogen bond. Alright, so make sure that you listen to this video and you complete the assignment that goes with it. We will just talk a little bit about this topic in class, but I think we'll not talk about it much. So from the video, from the assignment, I think it should be good. If you have any questions, bring them to class. Thank you.